Hi there. Welcome to our bug hunt. Thanks for participating. I'm Philip. I'm one of the core engineers on Firedancer, working on Firedancer mostly. And along with my colleague Michael, we're going to give you an overview of the Firedancer code, the code that's relevant for the bug hunt, and give you kind of some high-level orientation to help you get started. Firedancer, since it's such a piece of high-performance software, it, it touches on a lot of pretty important concepts and pretty low-level concepts in operating systems and hardware and networking. So, and we're going to run through all that quickly. So hold on to your seats. But first, before we get started, I'll talk a little bit about what Firedancer and what Frankendancer are. So it's a new validator for Solana, but what even is Solana and what is a validator in the first place? Well, Solana is a blockchain, proof of stake blockchain, permissionless, running. It's been around for a handful of years. It's one of the top blockchains. And validators are the software component that basically runs the blockchain. So it's run in a decentralized way by thousands of people around the world on their own hardware, and it receives transactions and decides which transactions will become part of the canonical chain, which transactions will actually happen. And then in addition to this, it also receives the transactions that other validators are sending and make sure that they're all following the rules that are required for consensus. It votes and achieves consensus on the history of what transactions have occurred, and that's what keeps the chain progressing. So then, if that's what a Solana validator is, right now there's one called Agave, and Firedancer is more or less the second. It's a new validator client, like I said, and it's written in C from the ground up for performance and for diversity. Okay, Michael, do you want to talk about the difference between Frankendancer and Firedancer? You're muted.
Yeah, so I guess we have, a long-term goal with Firedancer, which is to re-implement the entire validator stack top to bottom. The validator, software consists of a bunch of components. There's a gossip piece that's talking to all these other validators and figuring out where, they're located on the internet. There's repair pieces that are talking to each other and trying to receive data that they missed and so on. There's probably 10 or 20 of these distinct pieces. It's complicated to implement all of them, especially all at once and roll out a new validator. So we're kind of taking a piecemeal approach with Firedancer where we're implementing only part of the validator first. This is called Frankendancer. So we've lovingly termed it. Frankendancer is a stepping stone where we re-implement the entire leader pipeline. So there's kind of two operating modes for the validator. You're either the leader, in which case you're the person kind of receiving all the transactions at the moment and proposing a block, or you're a non-leader, a replayer, you might say, and you're receiving this leader's block and validating that what they did was correct. So most of the time you're a follower, checking the leader's work, but every now and then you become leader. So this is a part we decided to replace. It's an interesting part to replace because the performance of the network is somewhat dependent on the performance of the leader. We assume that you can kind of verify the work a little bit quicker than you can produce it. And so if we can improve the performance of the block production, then hopefully that might make the network faster. So Frankendancer is essentially replacing this leader pipeline when that does block production. Kind of at a high level, the components there are the networking layer. We've replaced top to bottom with an XDP, kind of not entirely kernel bypass, but somewhat kernel bypass stack. The networking, we have a quick protocol reimplementation that integrates with this networking stack to serve client connections via quick. We have reimplemented signature verification. We deduplicate all the transactions. We've, and we implemented the proof of history component, which we'll talk about a bit later. The shredding, which is about data distribution and data formatting when we go out onto the wire. So those are some of the high-level pieces we've implemented. It might be useful, I think, now to just kind of look at the boot sequence of Firedancer and how it works. It's kind of one important thing for security. So I'm going to present here my screen, and I hope this works. Okay, so Firedancer kind of produces one binary. It's called FTCTL. Pretty much all of our commands are subcommands of that binary. So you pretty much just need to audit this one binary. And when we've determined the scope of this audit contest, it's pretty much everything reachable in the production version of this FTCTL binary. So there's a lot of code we've written for the full Firedancer that isn't included in Frankendancer. These are things that replace the components that aren't yet fully written or aren't fully integrated. That is all out of scope, but it's mostly this leader pipeline that we've implemented that is in scope, as well as the FFI, the foreign function interface that connects this new code to the existing Agave validator. The code that was already in the Agave validator as written that ships in production today as part of the existing validator is not in scope. They have their own bug bounty program that you can submit to if you have interesting findings there. So when we look at the boot sequence, we have this FTCTL binary, and we have, I guess, a main function somewhere. Here it's called main1 for linking purposes, but so we come in and we select a subcommand. The main interesting subcommand is this run action. There's a couple others. There's a monitoring binary, which or a monitoring command, which can monitor the running validator. There's a command to set up some keys and things like this. But pretty much the only main command is really run. And this has a somewhat sophisticated boot sequence that runs Firedancer. There's a nice comment here that explains it, but essentially we spawn the run process. This creates a child process, which is a PID namespace in Linux. Firedancer only runs on Linux. This PID namespace serves as the root process then for all the child processes. So if this PID namespace ever exits, the kernel will terminate all of the children of it. And this PID namespace is also going to watch all of the children processes. So if any of the child processes terminate, this PID-NS will also terminate itself and bring the entire process tree down. So everything kind of boots together and then exits together. You can't get any stray processes here. So we come into run Firedancer here, and there's some simple initialization that happens. We know we install some signals, but the main thing that's interesting is we're going to boot clone Firedancer here. This, is going to clone this main PID namespace, which is a new PID namespace as we discussed. And this eventually, you'll see a lot of stuff around pipes here. This is kind of just connecting things so that they can terminate at the same time. In Linux, it's a bit annoying to track if a child process died properly. So we have pipes that will signal if the child dies. Eventually, we have this for loop. And what this is going to do is go through these things we call tiles and clone a new process for each tile. So talking about a tile gets us into kind of the high-level architecture of Firedancer. It is a one thread per CPU core design for high performance. So every CPU core has one thread that just spins in a loop and does work. There's no kernel scheduling. There's no, threads getting context switch in and out. There's one thread per CPU core, and Firedancer actually takes this a little bit further. We have one process per thread. So every thread lives in its own process. Each thread does a specific type of work. So some threads do signature verification. Some threads do transaction execution. And so the kind of Firedancer architecture is consisting of a bunch of these threads that are all connected together through shared memory queues. And the leader pipeline that we've created is a pipeline set of work that basically receives network packets ingress and produces network packets at egress, and then has a bunch of threads that sit in the middle that pass data from top to bottom. So each of these tiles we'll talk about more in detail later, but at least for the boot process, it's enough to know that we go through each of the tiles and we clone a new process, a new child process of this PID namespace that is going to do a specific job specific to whatever that tile is. These processes actually get run with execve, so they get their own address space layout, randomization, and everything. Okay, so when these tiles boot, we're going to execve the same binary, but with some special arguments that cause it to enter this run one sequence. This is a tiles boot process. So each of these individual worker functions we call a tile. The signature verification one is a good one as an example. It pretty much at a high level just looks like while true, verify an incoming transaction that the signature is valid, and then send it on to someone else to execute it and send it out on the network or pack it into a block. So the way this signature verification tile would boot is it comes in here and it has, sets up some CPU affinity to run on the right core and everything. It actually clones again. This is so it can get a huge page-based stack for performance reasons, but eventually comes to this tile main, which is going to run the tile itself. This is part of our topology functionality. A lot of security things here. So the main thing that's interesting is there's kind of two things interesting from a security perspective. So one, it calls this privileged init function. This is happening prior to sandboxing. So Firedancer has a very thorough sandboxing model where we, prevent system calls from happening. We'll look at that in a second, but the tile is allowed to execute some code before it gets sandboxed. This might be privileged operations. One example is the networking tile. If we come in here, all the tiles are in this directory. It's going to have this privileged init function. It does some privileged things. Mainly, this is initializing XDP, which is the networking stack, which uses a bunch of syscalls, bind with the sock raw socket, and so on. A lot of tiles just read the public key during this. We have a signing tile, which is going to have a privileged init, which is just going to read the key and then protect that memory so it doesn't get dumped. But coming back to our tile runner, so we do this privileged init. No, sorry, this is the wrong function. Well, here's the topo. Here we go. So we do privileged init. One other thing we do before entering the sandbox is we join the tile workspaces. So in Firedancer, all memory is allocated out of what we call workspaces. The workspace is kind of conceptually, it's a data format that sits on top of shared memory. So in Firedancer, all memory is shared memory. We allocate out of gigantic and huge pages from the Linux kernel. So we don't call malloc or anything. We actually explicitly at application boot go and create a bunch of gigantic 1 GB pages and several huge, which are 2 MB pages. And then we map them into the relevant tiles. So remember, each tile is its own process. So each tile is going to map just the memory that it needs for the data it needs to access. And it'll map them read or write depending on what it needs. So as an example, the signature verification tile maps as read-only from the networking tile that's giving it network data to verify. And it maps as writable its output links, which are sending data, to the block packer. The block packer will map those output links as read-only. So we have this join workspaces function that is kind of going to compute all those read-write mappings and figure out where things are located in which shared memory. So that shared memory is broken down into a bunch of files that kind of isolate it in terms of permissions. So that happens while we're so-called privileged. We do the privilege init, which is tile specific. We check a few things around, which file descriptors are allowed. And basically then next we're going to call sandbox enter. So every process enters the sandbox once it's done this privilege initialization step. The sandbox has several steps, which we can run through very quickly, very important for security. They're described in this ftSandbox.h file, and ftSandbox.c kind of implements a lot of the functionality. The environment is totally cleared and securely overwritten with zeros. We check the list of open file descriptors to make sure there's nothing, not a stray open file, like etc. password making it into the process. We check a bunch of things. Controlling terminal is reset, so you can't send signals or write to the TTY. Eventually, we're going to switch to a user ID provided by the operator in the configuration file. We use a bunch of Linux namespaces to isolate things further. We can keep kind of going down the list. The main thing that's actually really important here, though, is the setcomp BPF filter. So we're going to restrict in every tile, aka every process, the system calls that are allowed from that tile to just the ones that are necessary. So this is a whitelisting approach. If we go and look at, for example, the networking tile, these are all in these so-called setcomp policy files. These are a domain-specific language specific to Firedancer. We have a compiler that turns this into BPF bytecode. I think it's under the generated folder here. So if you look at net-setcomp.h, yeah, this is the generated setcomp code. We've had this generated code audited, but this DSL, we haven't really audited this. It's not as important as verifying that the instructions produced are correct. So here's the system calls that are allowed for the net tile. There's pretty thorough documentation of why these syscalls are allowed. We allow write only to the log file instead error. This is for logging purposes, same as fsync. Um, the net tile in particular has some networking related syscalls to send and receive packets. Because we're using XCP, actually the packets come in mapped memory ring buffers. These are just to tell the kernel that they're, we read from the ring buffer, and so it can repopulate or send messages that we put into the buffer and so on. So net tile has quite a few, well, not quite a few, quite a limited set. But if we look at some of the other tiles, they have even less. Pack, for example, or signature verify. Verify here is signature verify. It literally only allows write to the log file or std error or fsync to the log file. So most of our tiles are secured in this way with setcomp, so an attacker couldn't make the calls that they're not allowed to. I think that mostly describes kind of the boot sequence. If we come back to the topo tile run function here, so after we enter the sandbox, we're basically just going to call unprivileged init, which is tile initialization that is now being done within the sandbox. And then we go and call this fdmux tile. This is pretty much a while true loop. That's just going to dispatch work to that tile. So if we look at the verify tile, it provides these callbacks to the mux function to tell it how it wants to do the work that it's going to do. And then the mux function is going to call these. Pretty much the mux functionality, all it's doing is it has a bunch of input links. These links are shared memory queues. I think Philip will describe these in a moment. But it's going to read from these links in a round robin kind of fashion, and then process the data that it received from the link, and then maybe produce some output, send data downstream. So here, this verify tile, you can see after it's received some data from a link, it's probably a transaction. It's going to actually pause the transaction and then probably somewhere actually verify it. Here we go, fdtakes and verify. It's going to verify the transaction. I believe that kind of covers the boot sequence. We talked a lot about sandboxing. There's a couple other things that are interesting, I think. So the topology that describes all of these tiles and how they're linked together and which memory they map. Some tiles map things read-write. That other tiles also map read-write because they both need to write to them. It's interesting from a security perspective is this fdfrankendancer.c file. This kind of has a little somewhat C-based declarative language that describes what we call the topology. So this is all of the workspaces, which are the files in shared memory that have their own read-write permissions as they get mapped into different tile processes. Here are all the links between these tiles, which Philip will describe. Here's all the tiles. And each tile runs on a specific CPU. It might write to certain links. And then each tile consumes from certain links or ring buffers. So each tile is kind of has all of its input links specified here. So this is the topology, also kind of useful to look at. There's a few other things that are interesting for the sandboxing, I think. There's this FD key guard. Firedancer keeps the private key isolated to one specific tile, which we call the key guard or the signing tile. Other tiles can load the public key, which they might need to verify certain things, but only the key guard has the private key. I think with this sandboxing, the thing we want to highlight that's really important is all of the tiles are kind of their own security domain. So breaching a link between the tiles is we consider very serious. So for example, if an attacker is assumed to have code execution on the networking tile, the networking tile connects through shared memory to the quick tiles, which are implementing this quick protocol. So if, let's say, an attacker got remote code execution on this networking tile, if they can jump through some primitive or some exploit they find to gaining code execution on the quick tile, that we consider kind of a sandbox escape. These tiles are supposed to be totally independently sandboxed, separate processes, from each other. I suppose there's one other thing that's interesting here with the sandboxing is, it might not even be code execution. It might be data exfiltration. That is a problem. We've tried to protect the signing key by isolating it to this signing tile. You can imagine an attack, where maybe they don't gain code execution on the signing tile, but an attacker is able to get code execution on a nearby tile and perform some sort of timing attack or cache invalidation attack or anything to measure in an attempt to reconstruct what the signing key was, and then if they have access on the networking tower, they could exfiltrate it to a remote server. So we also consider those very important vectors to look at and be conscious of. I think I'll hand it over to Philip now. We've talked a lot about the tower communication to describe what's involved in that.
Sure, let me also share one sec.
Oh, do I need to end mine?
No, I should be good. Um, okay, so as Michael mentioned, all our tiles are connected by links, and these links are implemented in a library called Tango, since it's about interfacing between two tiles, like a Tango with two people. Um, so it, and there's basically the links are implemented as a mcache and a dcache pair. So it's the metadata cache and data cache. So basically, the mcache is a ring buffer, single producer, multiple consumer, concurrent ring buffer, and dcache is basically just a big piece of memory that's used for the actual data, the payload of the messages we're sending in the mcache. The mcache is, um, like I mentioned, a ring buffer. Each entry in the ring buffer is this frag meta t struct that I'm showing right here. And so it has a sequence number, and then the chunk, which is basically like a compressed pointer, size, and some other information that's not as important or not as critical. The SIG, which is used for fast filtering, so a consumer can quickly tell if they care about the data that this mcache line is referencing or not, or they can just skip it. Um, so yeah, tiles, there's one producer, it writes to an mcache, and then each tile typically writes to one mcache, can write to, or if you write to a little bit more than that, then the tiles pull a bunch of different input mcaches looking for new messages from their predecessors or the tiles that come before them in the topology. And then as soon as they get a new fragment, then they go and process it. The mcaches and dcaches can work in either a reliable or unreliable way. That's with flow control turned on or turned off. For most of the links that we have here, we've turned flow control on, although we've also tried to build our code to, uh, so everything assumes that flow control is off, even though in some places it's actually on. And the way flow control works is with a credit-based system. So the producer knows how many credits it has, like basically um, how how much is the slowest consumer lagging. And so it also knows the size of the ring buffer, and so it will wait and not produce something if it might, or if the next message it would produce would overwrite something that the slowest consumer might still be reading. Um, okay, maybe I'll walk a little bit through the mux tile first. This is kind of like the that hosts all the other tiles. So as Michael mentioned, here's the giant while true loop that starts here, and what comes first in the code is housekeeping, which periodically with some random time picked in a very careful way. We send heartbeats, we update sequence numbers for our incoming and outgoing links to help with flow control, copy metrics. But the main work begins after that. So at every iteration of the while true, we check, or we have a option for a callback. We check if we have enough credits to send, if we won't overwhelm our slowest consumer. And then if we do, again, we call another callback, the after credit callback. Then we look at the incoming or the input links, and we see if we have any new messages on this link. If we're caught up, then we just go back. If we've go back and repeat. For overrun, we which can only happen in um, the unreliable mode when flow control is disabled, then we handle that. And then otherwise we have a new fragment, a new message, and so we handle it and then again check if we were overrun, do some final processing, and then repeat. So that's the, every tile is pegged at 100% CPU, running this loop over and over again as much as possible, reacting to work that's coming in and producing work for other tiles. Okay, I'll dive into a few of the tiles themselves. So all the tiles are located in, as Michael mentioned, app fdctl run tiles, and a lot of the tiles call code in a lot of other places in the loop, but this is where you can see the callbacks defined that the mux tile that I will call these callbacks I just mentioned. So, actually, Michael, do you want to start with the net tile, maybe?
Yeah, sure. Let me share again. Yeah, and we'll describe these probably in order, in pipeline order. Again, we described kind of this pipeline where we receive transactions from the network, and we do a bunch of work to verify and pack them into a block as leader, and then we produce a block, and that's going to go out again to the network. So this forms a pipeline. FDNet is the ingestion point for this pipeline. It kind of defines these callbacks it has down here, but pretty much all it's doing is receiving packets from network packets from a ring buffer that's memory. It's memory we allocated probably out of the network device driver. It depends on the setup of the kernel and how the user has configured XDP. But in the optimistic case, it's shared memory. It's somewhere in the network device and has a ring buffer of messages. And so we're going to read messages out of there, copy them out, update some, counters kind of saying that we read the message so the driver can kind of continue. And the network tile also handles egress. It kind of does dual functionality at the moment. So people can also send packets to the network tile and it'll push them out onto the network device, also via what's called an XSK. But this is kind of again, a ring buffer that goes into the network device. If you look, you'll see there's this after frag. This is kind of doing the sending. So it's also computing a bunch of it. So yeah, XCP is a raw packet interface, so the kernel doesn't really fill in any information. So we also have our own app implementation to compute destination MAC address for the gateway the packets will be going out of. Not too much really that interesting here. Yeah, so networking tile, yeah, it's handling all this network interfacing. There's probably just gonna be one of these tiles. It's pretty high performance. So networking tile sends to FD-Quick, which is our implementation of the Quick protocol. Solana uses Quick for receiving transactions. Originally, they used to use UDP, but ran into some problems with that. I think it's susceptible to denial of service because clients aren't authenticated. There's a few other reasons they switched to this. So Firedancer has our own quick implementation that we've written. You can find that under FD Waltz over here and under Quick. This is a pretty large surface. Quick is a complicated protocol, so there's a good amount of code in here. This is implemented from scratch. So the Quick tile pretty much receives network packets from the net tile, and it's going to kind of parse them as quick messages and turn the Quick state machine to figure out if a connection should be reset or if some response or to a ping should go back out or anything like this. The Quick tile, as its output, produces fully well-formed packets. There may not be valid transactions, but at least in the case where the client sent a valid transaction, it will be. So the Quick protocol is going to produce these maybe malformed, but hopefully not transactions that it sends as output to the verify tile. You can kind of see the basic shape of a lot of the tiles here in the quick tile. The net tile is a little special. So it has a during frag, which is as it receives a fragment from the networking tile, as it receives a packet, it are you muted maybe? It's going to copy that packet data to a local buffer. This is to ensure that the networking tile, if it's compromised, can't modify this buffer while it's being processed and cause some kind of corruption. So it copies this to a local memory area that's inaccessible to the net tile. And then after the packet's been fully received, it is going to check what port this packet arrived on and like forward it to the right place. So in one case, this is the quick kind of handler. In the other case, it's this UDP, this raw UDP transaction handler that isn't implemented with quick. Continuing down the pipeline, we have FD verify. This is the signature verification tile. We talked a little bit about it before. Pretty much it receives transactions from the quick tile, and it just verifies that the signature, that it's signed by the right user. So someone isn't trying to like send, a transfer from account A to account B and they're not in possession of the private key of account A. That's basically all the verify tile does. It also deduplicates transactions. In Solana, there's a lot of users send the same transaction repeatedly. And so it's useful to filter those transactions early because signature verification can be expensive. From the signature verification tile, everything gets sent to this FD dedupe tile, which is another deduplicator. The reason we have this is that you'll probably be running a lot of signature verification tiles, perhaps 20 plus of these, to get a lot of throughput. The signature verification is kind of expensive, and so if the same transaction went to many different verified tiles, we want to deduplicate it again so that there's only one that makes it through the rest of the pipeline. So we have this dedupe tile. From dedupe, we go to pack, which I think Philip can talk about as he wrote it.
Sure. Let me share again. So the pack's job is to receive the deduplicated transactions and then decide which ones will actually make it onto the chain in the block that the validator produces when it's leader. So it's the block space is limited, and that's a constraint. And you may have a lot more transactions that you can pick from than you have space for, and so you need to do this selection of transactions. And in particular, you get some of the fees from the transactions. So a validator wants to select the ones that will be the most lucrative for it. So Pack, here Pack has kind of two parts. One is the tile that handles all the interfacing with the M caches and D caches, and then a lot of the logic, which is it's probably the most complicated logic-wise tile that we've seen so far. It's located in Ballet Pack. So they're basically two parts. One is this inserting of a new transaction, where you do a bunch of checks and then you evaluate how you compute the fees that it will pay and how much compute it'll use, and then what transaction or what accounts it writes to, and you insert it into a big treep. It's basically a heap or a priority queue. And then the other main part of Pack is when you actually go to schedule a transaction. So you iterate through the heap and see what doesn't conflict with other transactions that are currently being written to, and you remove it from the heap and schedule it. So if you haven't noticed already, there are a lot of complicated data structures with a lot of invariants that have to be preserved by this whole delicate process. We've there's also expiration and a few other smaller features. There's a validate function on here that validates a lot of these invariants. So if there's a way to break any of the invariants, then that would be something we're definitely interested in. Okay, so then Pack sends these groups of transactions that don't conflict called microblocks to, let's see, well, it sends them, here. to the bank tile. And the bank tile is the first tile that we've encountered in this presentation that's actually not fully implemented in C. So the bank tile executes all the transactions. And because for Frankenanswer, we haven't built that code out yet, it uses the Agave VM and Agave execution engine for all these transactions. So it executes them with FFI, and that means um, it actually lives in the same process. It doesn't live in its own process like all the other tiles. It lives in the same process as the rest of Agave. Um, Michael, do you want to talk about this, or should I keep talking about it?
Yeah, I can touch on this a bit. So what Philip was mentioning is pretty important about how bank lives in the Agave address space. So we talked at the beginning how all of the tiles live in their own process and are very heavily sandboxed and so on. This is mostly true. It's true of the code that we've written for Firedancer, but when we do FFI with Agave, we have to interact with the existing validator code. That validator does not sandbox itself. It doesn't have a lot of functionality to sandbox. And so that validator runs as a child process of our PID namespace, but it's not an isolated piece of functionality. It's all of the remaining code. Um, it's unsandboxed. There's no set comp filter, and so if you can gain code execution in that address space in that process, then you have full access to the host operating system and everything else that entails. So most of these tiles that are doing FFI have to live in that Agave address space, and so this bank tile is one example of a tile that lives there. It doesn't. It is unsandboxed, and so an attacker, if they're able to get somehow, from a networking, from the parser in the networking tile being compromised all the way through to the bank, then they may be able to read the validator's private key or do other things. If we look quickly at kind of how this FFI is implemented, maybe I'll share my screen. You can kind of look in the code base for these FDX functions. These are all the functions we've implemented to do FFI. So pretty much when we come into the bank tile here, when it gets a group of transactions to execute, it's going to call some FDX function here, FDX bank load and execute transactions. This lives in Rust. It has a CABI, and this is going to then go and call some existing Agave code in the same address space as Agave to execute these transactions. I guess, oh, here it is, bank load and execute transactions. All of the FFI looks like this, so it's just some, a raw CABI that's being called back and forth. Yeah, so the bank is pulling a few FFI functions. It also manages, it has to increment some reference counters to keep these objects alive and so on. But there's a pretty complicated piece of code here doing transaction creation. So as we mentioned, we kind of have these transactions coming in from the network that have been verified and so on. We're executing them in Rust, and Agave expects them to be formatted as a certain kind of object. I forget what it is. It's somewhere in here, this sanitized transaction object. So this has a bunch of kind of nested things. It's kind of a parsed representation that they have of one of these transactions they received on the wire. We've re-implemented this for performance with this bank ABI ticks and a net function. It's not pretty, but this is constructing a Rust compatible, like an object with the Rust ABI, essentially, that looks to Rust as if it were a Rust object. So we populate all these, fake vectors that kind of have a length and a capacity, but aren't actually backed by the Rust allocator and so on. This is how we create the transactions really, really quickly for use in Rust, get high performance, and then we pass these objects over the FFI boundary. This is kind of the only place we really do this. For the most part, we kind of let Rust be Rust and just, have a very, very minimal FFI interfaces. So this is the bank tile. Once it executes all the transactions, they're either going to succeed or fail. In Solana, failed transaction still gets included in the block usually because we want them to pay fees. So we prove that the transaction failed. So these micro blocks then get sent from these banks. They're probably going to be a lot of bank tiles. Again, these are executing transactions. We can probably parallelize this work. from bank, the transactions go over to POH. So bank tile was somewhat simple. Again, it's mostly leveraging code that was already existing in Agave. The proof of history tile is less simple. It's re-implementing this so-called proof of history protocol almost that the Solana protocol is a parent of. There's a pretty long comment up at the top here that might be useful to read if you're trying to understand proof of history. Essentially, proof of history is kind of trying to act as a system clock. The main functionality that it implements is if one of the leaders is asleep or their computer's turned off, the following leader needs to be able to prove to the network that they waited for that person to publish something and they never did before they publish their own work. And so this is done by just hashing repeatedly. If you can hash a certain amount of times, you can kind of say to the rest of the network, oh, look, I waited long enough. I did all this work. So, this computer must have really been turned off, the one before me. Unfortunately, the way it's woven into the block production is kind of much more involved than what we just described. So you need to tag all of your micro blocks with a special hash as you're spinning this machine that's computing all the hashes, and it gets very involved. So this we won't talk about all the functionality that it does, but the main thing is it's receiving these micro blocks, these groups of transactions from the banks, and it's sequencing them with respect to each other. So there's one stream of micro blocks, and then it's tagging them with a special hash, kind of saying, hey, this is how far it was into my block. And the way it tags them is so that one other kind of goal of Solana is that the verification can happen in parallel. So even though producing a block needs to happen in serial, someone else can verify all these hashes very quickly. So it kind of periodically stamps a new hash so that each of those, from point A to point B can be verified very quickly if they're all done in parallel. So POH kind of receives these microblocks from the bank. It also sends microblocks just with the additional tagged information. Those microblocks are going to go out to the shred tile, which Philip, again, can talk about a bit more.
Sure. Let me share again. So as Michael was saying, the shred tile gets a bunch of microblocks, and it it batches them and then cuts them up into networking packets called shreds. That's a whole Solana specific protocol. It does some forward error correction and builds signs the shreds basically. And in addition to this, the shred tile has another job, which is that it receives shreds from the network for when you're not leader, and it does a bunch of validation on those shreds. It parses them, and it forwards them. So there's a complicated protocol called Turbine, part of Solana, in which that's used for distributing the blocks that the leader produced. So it builds basically a tree of validators where you receive shreds and then forward them, and the tree is generated pseudo randomly and varies based on the shred. So when you're not the leader, you're almost always receiving shreds and forwarding them. And then when you are the leader, you're building the block and then sending those shreds to where they need to go in the tree. So let's see, there's so these shreds that get produced need to go to two destination, or they need to go out to the network, and then they also need to go to the final tile, which is the store tile. Store tile again is simple. It's kind of like the bank, mostly FFI. So it basically just calls this FDEXT tile to insert shreds into the persistent on disk block store that's existing in the Agave code.
Yeah, so there's a nice diagram of kind of all these tiles and how they connect together, which maybe we can pull up, Philip. This was
Yeah, do you want me
produced,
to show it?
yeah, this was produced by Neodyme, one of our security auditors, who's produced a really useful report, which you can also read. I think it's linked from the contest page, but it's also in the Firedancer organization's GitHub under audits. They describe a lot of this architecture in more detail in this PDF, but they've produced here this useful diagram of the entire flow of data through these tiles. There's a couple other tiles worth calling out here that weren't part of the pipeline in a trivial way. One is the signing tile we mentioned a bit before. So this is the only tile that hosts the validator's private key, at least the identity key. So anybody that needs to do signing operations to produce, ED25519 signed data will have to send a message to this tile over one of our primitive, over an Mcache primitive saying, hey, I'm requesting that you sign this, and they'll get back the signed data. Quick, DAO signatures to prove to peers that it's in possession of the validator's key to get QoS on its connection. The shred tile signs outgoing shreds. So there's a few cases where tiles connect to this signing tile. There is also a metrics tile that receives data from all the other tiles. All of the tiles collect metrics, how many transactions have failed to verify and so on for performance measurement. So this metrics tile collects all of that information periodically and serves an HTTP Prometheus compatible endpoint. This endpoint will probably be configured behind a firewall, but it might be interesting to look at. So, it formats this as a HTTP endpoint, and there'll presumably be some monitoring tool that'll periodically scrape this and put it into a database. I think that's all of the tiles, unless we forgot one.
No, I think we got everything.
Yeah, the signing tile is interesting for one other reason. It is not part of this pipeline, but also
Sorry.
kind of operates a little bit out of band. So it doesn't, we describe this mux loop where tiles read incoming fragments and then send outgoing messages. The sign tile is not part of this, not pipeline. So it actually blocks the tile that's calling it. So if the quick tile wants to sign a message, it actually just sends it synchronously and waits for a response rather than kind of having this queuing, and message passing primitive system like the rest of the tiles do. I think that's all the tiles. Probably at this point might be useful to talk about some of the vectors of attack that we are particularly interested in. If we don't know about one of the vectors, that's even more interesting, perhaps. But some of the ones we do know, a signing key leak is probably one of the more important ones. We've tried to get the signing tile really isolated in the memory of this one particular tile. To get to it, you might have to compromise another tile and then use a timing attack or use some exploit you might find in the communication primitives to that tile to try and exfiltrate the key out. Any signing tile information leak or exfiltration would be really interesting. Sandbox escapes. I want to stress again, we talked about it earlier, that you can assume some level of privilege already to demonstrate a sandbox escape. Even if you have code execution on a tile and you use it to get code execution on another tile, that's really interesting. Probably within the Agave subprocess is not so interesting because there's no sandbox there. But being able to do these hops between tiles is very interesting. If you can escape the sandbox somehow, right? Use one of the syscalls we've allowed or bypassing one of the protections we have. I think the sandbox, we've tried to make it very strong, but if there are additional mitigations there that you think of that are useful, we'd probably be happy to hear about those. Consider it as an insight level finding. If you can provide good feedback on that design, even without breaking it. So yeah, sandbox escapes, another particularly important thing for us. Denial of service. So the validator needs to be available, right? Otherwise the network will go down, especially if we have a lot of stake. There's probably two kinds of denial of service. You could say there's non-distributed, so it's local just to one validator. So if you can cause a Firedancer validator to spin in a loop or DOS the quick protocol in a certain way, then that's going to deny service to everyone. We're not going to be able to produce a block. The denial of service that you can do against all of the Firedancer validators at the same time, like sending a certain packet to them that causes them to crash, or like doing something with the consensus protocol that causes them to crash or spin in a loop and be unavailable, is really, really bad because that'll crash the entire network rather than just one of the validators. So any denial of service is pretty interesting. Behavioral differences, right? We're re-implementing a consensus protocol. Largely the consensus parts have been left to the existing validator. So there may not be a ton of surface area to find these, but there are some cases where it could happen, especially the block production. So you could cause Firedancer to produce a block that is not accepted by the existing validators, right? If we produce an invalid block or we accept a transaction that wasn't signed correctly or anything like this, you're going to be able to cause us to produce blocks that don't make it on the network. uh, there's possibly avenues depending on how we receive transactions or data. I mean, we do receive shreds via our new code, which is the initial ingress point for replaying data from other validators. So if there's some bug there, potentially it could cause a behavioral difference in how we replay things and cause us to fork. So any of these kind of forking attacks are pretty interesting. Uh, Regarding the invalid blocks, there's, I think, probably an area where we're very interested in since that's kind of the main functionality of the parts we've re-implemented is the block production, and some of it is quite involved to get right. Specifically, the pack tile that's kind of producing these micro blocks, and the POH tile that's computing all these hashes and trying to get mix the hash in with the hash of the block and so on. There's a lot of invariance and a lot of complexity to that, just inherent to the protocol. Um, I would make kind of remark like there's some obvious attacks here against the implementation of Firedancer. It's written in C, so maybe you would find a buffer overrun in the network parser, that allows you to get code execution on the networking tile. You might think these are like the more interesting kind of attacks. I kind of have a sense that the more interesting attacks are more systems level and at a protocol level against things like PAC and POH, right? It's finding ways that the invariants there are broken, and finding, maybe the credit management is off by one, and you can cause one of the tiles to overrun another tile and read partial data, and then it verifies something that isn't valid, right? It's more of these like kind of logical issues that may be more interesting. I think that kind of covers most of the attacks we're interested in. And then, Philip can talk now about the risky areas of the code that may, enable some of these attacks.
Yeah, thanks. So, I mean, Michael, you covered a bunch of that, but we definitely have some parsers which are known to be hard to write in C. We have, is filled with parsers. There's also the transaction parser, which maybe let me point out where some of these are located. Um, so as Michael had mentioned previously, Quick is mostly located in Waltz in the top level. So yeah, there are a lot of parsers there. In Ballet, TXN is the transaction parser. Parsing untrusted user input. There's the shred parser, which is shred here, shred parser, and then also the shreds get kind of like parsed at a higher level in the FEC resolver here. So it's a lot of validation of things towards the bottom. Yeah, a lot of validation of untrusted user input. So if we get anything wrong there, that could be potentially risky. There's, in our metric server, we have HTTP. Again, that's a little bit lower priority because it's unlikely to be exposed to untrusted user input, but that's still, pretty important. HTTP is a relatively complicated protocol. We also have a bunch of reimplementations of cryptographic primitives. So these are mostly in Ballet. For historical reasons, we have some things that are not cryptographic protocols in Ballet, but AES, Blake 3, binary Merkle tree, Cha-Cha 20, ED25519. We put a lot of effort into this. It's extreme performance, and it's a spec that's pretty loosely specified in some spots. And it's pretty important that we match exactly what the Rust crate that Agave uses for that. Here's HTTP, read Selman, SHA-512, a bunch of crypto reimplementations. As we mentioned earlier, there's all the FFI code, which also is pretty interesting and unusual from a security perspective. And and those are some, we have a toml parser as well. That's used for the configuration. Again, it's trusted user input, so it's a little bit lower risk, but we would still like to have that, not like to have any issues there. We're still interested if there are any issues. Um, all right, so I think to wrap up, I'm just going to give kind of an overall layout of the code. Um, it's something that we've been working with for a long time, but files can be kind of all over the place. Or at least, it may not be obvious when you first start why things are where they are. So I guess, as with most of these projects, most of the code is in source, although we have like all the make files and things like that in config, so that can be useful too. The build goes to, or the output goes to build typically. Okay, and then app fdctl, this, builds the fdctl binary. This is kind of where the main is located and a bunch of other, the tile code Michael talked about, a bunch of the high level things that kind of kick everything off. Again, as I said previously, Ballet is mostly implementations of crypto things and encoders and decoders, although there's also, for example, pack is here for some historical reasons, and shred parser and the transaction or base transaction type. Disco has a bunch of tile specific code. So, each or some of the tiles have a directory here under Disco, and like, for example, Shred has a bunch of helpful, helper classes basically. Flamenco is mostly, well, it's, yeah, mostly not in scope for the audit other than the leaders. This is where a lot of our components for the full Firedancer, which reimplements everything, goes. But we do use this one leader schedule computation. Funk is again out of scope for this. Tango has, IPC primitives, basically mcache and dcache that we talked about earlier. So sequence numbers, flow control, CNC, command and control. Util is, what you'd expect, a bunch of utility functions. Here we have actually a fair amount re-implemented, math and logging, IO, histograms, a nice SIMD wrapper, and here's where the sandbox is as well. Waltz is mostly for networking communication, so we have, Quick, which uses TLS, and our XDP implementation is here. Wiredancer is our hardware SIG verification code, so it's like Verilog code, not C. And again, I think this is not in scope for the audit, although we're happy to hear about it as well. All right. I think that wraps up our whirlwind tour of the Firedancer codebase. Again, thanks for taking a look at it. Thanks for participating in the contest, and we hope to hear from you soon, and we're happy to answer any questions in the Discord. Thanks.